Okay, so first let's talk about how to use a model kit. So your model kit should come with some instructions that are going to probably have a lot in common with a lot of other model kits instructions, but you know, I don't want to say each one's unique because there are some that are pretty much the same as each other, but there are some that are different. Just make sure you follow your kit's instructions because it's important that you use the correct atoms and the correct bonds because otherwise the geometry won't be right. So in my instructions, so we're going to build, we're going to use practice exercise 1 as a starting point, and we're going to build methane. So I'm going to show you how to do that. So if you look at my kit's instructions here, so under the atoms table, which is this table here, so methane is CH4. So first we need to figure out its hybridization because that's what's under this use column here. So hopefully, if you guys were asked to draw the Lewis structure for methane, which is CH4, you would come up with this structure that I drew up here. Okay, so if that's the Lewis structure, now we're going to try to determine the hybridization. So in order to do that, we need to determine the total number of regions of electron density. So a molecule can have two types of regions of electron density. It can have bonding regions or it can have lone pairs. Now notice I said bonding regions, not bonds. So a bonding region is a region between two atoms that are bonded to each other. It doesn't matter how many bonds there are. In other words, let's take this CH for instance. This is one bonding region, or one region of electron density. Now, what if you had this, for instance, acetylene? If you were looking at this here, this CH would be one bonding region. This CC would be another bonding region. That would just be one bonding region, though, not three, just one. And then this would be a third bonding region. So this molecule here has three regions of electron density. Okay, but we're not doing that one, so I'm going to get rid of it so it doesn't confuse people. Now here, we've got one bonding region here, a bonding region here, bonding region here, and a bonding region here. So that's 4 bonding regions. And how many lone pairs? 0. Gives us a total of 4 areas of electron density. Okay, so if we have 4 areas of electron density, that means that we are going to need to combine 4 atomic orbitals to get 4 hybrid orbitals, because the number of orbitals in equals the number of orbitals out. So that's pretty important. So orbitals in equals orbitals out, and that's equal to the number of regions of electron density. So that's going to be 4 in this case. Okay, so when we mix orbitals together, so we're looking at the valence orbitals. So valence orbitals in carbon, you've got the 2s, and we're just going to call it s, and then the 2p sublevel. And so we're going to start combining them with the lowest in energy first until we have 4. So there's only one s orbital, so it's definitely our hybrid orbital is going to have an s in there. And since there's only one, it's only going to be one s that we can combine. And then, so we need 3 more. And look at that. There are 3 p orbitals, the px, the py, and the pz. And we're going to use all 3 in this case because we need a total number of 4. So 1 plus 3 equals 4, so that's going to give us 4 sp3 hybrid orbitals. And so since it's sp3, that's going to be our hybridization there. Bearing in mind that that carbon in the center is going to be sp3 hybridized, I look here and I see it's the 3rd entry down. It's going to be, it says C4, basically 4 for my model kit's going to be the number of holes, because there are 2 black carbons, one is 4 holes and one is 5 holes. And since I want the sp3 hybridized one, I'm going to use the black carbon that's got 4 holes. And then hydrogen colors that, so hydrogen is white. So the white colored balls, I need 4 of those. I'm building CH4. Now I am going to take my central atom and I'm going to put bonds on there. So I need to figure out which bonds I'm using. In my model kit, there are different colored bonds, and each colored bond has a different length than the others. And so in my case, it matters which atoms are in the bond, because it tells you that in the instructions. So methane just has 4 CH single bonds, so I am going to use the pink, because it says under color, it says pink. I'm going to use the pink bonds for all 4 in this case. So I'm going to take my central atom here, and I am going to basically put the bonds into the holes. So I'm going to put my atoms, my hydrogen atoms, on the other end. So, okay, so there's my methane. So I'd like to do a conformational analysis example for you guys, and we're going to use butane. So in this example, here's our eyeball. It's supposed to be an eyeball. It's pointing to a carbon that's going to be the front carbon for our Newman projection, if we're drawing a Newman projection for this. And we're sighting down this bond, so the carbon directly behind it, which is this carbon, that's going to be the back carbon of our Newman projection. All right, so now let's look at this thing in 3D, and I also recorded a video with me building a model, so if you have trouble seeing this in 2D, that's okay, we've also got that. So, all right, but let's draw this out. So we know that these carbons are tetrahedral. They're all tetrahedral. So if it's tetrahedral, every tetrahedral carbon has 2 in plane positions and 1 wedged position, which is coming out at you, and 1 dashed position, which is pointing away from you. So these regular lines, those are in plane. So therefore, we know that because neutral carbon typically has 4 bonds, and this is not one of those super rare exceptions where it doesn't, plus it's tetrahedral, so it has 4 bonds. It means there are 2 hydrogens that aren't shown, and one of them has to be wedged, so coming out at you, and one has to be dashed. Now, they always point up and away from the vertex. So the vertex is the point of intersection between 2 lines right there. So each of these carbons that forms a point that's a vertex. So the hydrogens need to be pointing away from it, so they need to be up, but they're not going to be straight up because one's coming out at you, one's pointing away. So it's going to kind of look like almost a Y shape if you're viewing it from the front. So from the front, it would look like if somebody were standing and doing the YMCA dance, doing the Y part of the YMCA dance, and their legs were together. So their legs that were together would be this CH3 pointing straight down, and then the hydrogens would be like their arms. And of course, this is a headless person. And then conversely, this vertex down here is pointing down, so it's a valley, V for valley, because it's the tip of the V shape. So if the vertex points down, that means so must the wedged and dashed substituents, except one's going to be coming out at you. So down and coming out at you, there. And then down and pointing away from you is going to be the dashed one. That's our butane there. So if we're making this one our front carbon, and that one our back carbon, notice how on our front carbon has got 2 substituents pointing up and diagonal, whereas the substituents that are pointing down are in plane. Like you can imagine passing a plane like that through the molecule. It's going to bisect these 2 H's here, and these 2 H's, and those 2 H's. So now how we're looking at this though, if this is our front carbon and that's our back carbon, we're looking at it like this. So like that. And this is a staggered conformation. Notice how this carbon has substituents that are up and diagonal, and the one behind it, they're down and diagonal, so there are no 0-degree dihedral angles. So this is our front carbon here. So we're going to do our Newman projection. So when we're drawing Newman projections, we start with a dot, which is going to represent the front carbon, and we put a circle around it, which is going to represent the back carbon. Okay? So all of our Newman projections should look like that. Now we're going to rotate the front carbon clockwise. Okay? So if we're rotating the front carbon clockwise, it means the back one is not going to change. But any substituents coming off of this dot are front carbon substituents. So we said that this had a Y shape. So I'm going to go ahead and draw that. Okay? So that's my Y shape. It's not perfect, but close enough. And then this back carbon here is kind of an inverted Y shape. Notice if this CH3 is pointing straight down, this one must be pointing straight up. So that's going to be that CH3, and I'll fill in the substituents in a second. I'm just getting the shape first. So this is going to be a staggered conformation because we don't have any bonds that are eclipsing. In other words, they all have a dihedral angle of 60 degrees between the front and back carbon substituents. So this, that, and that are 60-degree angles. Okay, so let's fill in substituents. So we said we had a CH3 pointing straight down in the front and a CH3 pointing straight up in the back. So notice my back carbon substituents, by the way, are not coming off of the dot. They're coming off of the big circle. That's really important and a huge source of point loss for people. Because if you draw them all coming off of the dot, that means they're all on the front carbon, and that's wrong. That'll be a big violation of the octet rule. Okay, so if we're looking at this front carbon again, let's revisit those H's. So this one here, so imagine if we're looking at it this way, and this is the closed legs of a person doing the Y of the YMCA. It's fun to stay at the YMCA. This is going to be their left arm, and that's going to be their right arm. So this is their left arm. That wedge substituent, that wedge hydrogen is going to go there, and the dashed one would be there. And then similarly, this wedged one is also going to be on the left side of their body, except it's going to be down and to the left. So if this is the front, that would be here. That would be that wedged hydrogen. And then this dashed hydrogen would be there. Okay, so that's the Newman projection for what that looks like. Now let's get all the other conformations. So what you want to do, since we've established that we're not rotating the back carbon, let's just go ahead and draw our Newman projections with the back carbon substituents filled in as they are. And that's a good tip for avoiding point loss. Okay, so I'm not going to draw 360 because it's the same as 0. All right, so let's do this first rotation. So we're rotating it by 60 degrees. So we said this was a staggered conformation because you've got a Y shape in the front and then the opposite, an inverted Y shape in the back. So if that's a staggered conformation, when we rotate 60 degrees, it's going to become eclipsed.
So what would it look like if they were eclipsed? Well, so like I said, we're going to rotate the front carbon clockwise. So this is 0 degrees. So if we go from 0 to 60, so that is going to look like that. Notice how this line and this line, they're parallel. They can one's directly in front of the other. So if I was holding this just right, you in theory wouldn't be able to see the bond behind it. So that's what it looks like when it's an eclipsed conformation. Is you've got this sort of, I used to call it like the double-tailed dog from the Simpsons Halloween episode, but I think you guys are a little young for that. So that's what kind of shape you have when something is eclipsed, is this sort of, I guess, C shape. It's like a C that fell on its side, I guess, except now it looks like it's on its back. Okay, so that's 60 degrees.
So in order to draw an eclipse conformation, we draw the lines slightly offset, but we know that there's really a dihedral angle of 0 degrees. So we draw them slightly offset just so we can read things. Okay, so this H is going to swing down and eclipse that hydrogen. So that 0 degree dihedral angle right there, they're basically exactly parallel to each other, right on top of each other. And this CH3 is going to swing up and eclipse that H. And this H here is going to swing up and eclipse the CH3. Okay, now 120 degrees, since this was eclipsed, 120 is going to be staggered. So this H is going to swing down in between the two legs of the back carbon, as it were.
Now, if we do 120, we are back in a staggered conformation again. So that's what that looks like.
So this is another staggered conformation. It's a good way to check yourself. They should alternate between eclipsed and staggered. So that's going to be that H, and this is going to be CH3, and that's going to be the H that was up there.
Now 180 is eclipsed again. Notice this like C that fell on its side, that shape. Okay, and we said that was 180.
So we're going to be back to eclipsed. So let me draw the eclipsed shape. Okay. Now this H is going to swing down there. This H is going to come up there. And the CH3 is going to swing up and eclipse the other CH3. Okay. Now we do another 60 degrees, so we're going to go back to staggered.
Now we've got 240. So that's 240.
So we're going to have a Y shape again in the front. And this H, fix that dot, so it looks more like they're all coming off of the dot. So this H is going to go down, and that H is going to be up there. And then this CH3 is going to be up here on the viewer's right. Okay? And then one more.
So 60 is 300, which is going to look like this. There we go. So that's 300, which is eclipsed.
We're going to go back to eclipsed. So let's do the eclipse shape of that. So we've got CH3 is going to come down here. This H is going to go up there. And this H is going to swing up there.
360 should bring us back to what we started with. And it does.
Okay, so those are my conformations. Now we need to figure out the energy values associated with them. Okay, so you have those energy values in your lab manual. And, okay, so we have two types of interactions at play. Let's start with staggered conformations. So they can only have one type of interaction, and that's called the gauche interaction or the gauche-butane interaction, which is between, so it's got to be between substituents that have a dihedral angle of 60 degrees, which means we're talking about one of them is on the front carbon and the other's on the back, and the angle between them is 60. And they don't involve hydrogen. It's got to be something bigger than hydrogen. So even methyl hydrogen, we say that's 0. It has no energy cost, essentially. It's pretty tiny. Okay, so we don't have any gauche-butane interactions here because everything has hydrogen next to it. So this is a methyl hydrogen, that's 0. This one, HH, is also 0, methyl hydrogen 0, and HH 0. Okay, so I need to make a little table here. These are all in units of kcals per mole. Okay, so at 0 degrees, the energy is 0 kcals per mole. At 60 degrees, we'll worry about that in a second. Let's do the staggered conformations first. So at 120, what types of interactions do we have? Well, this is a methyl hydrogen, so they have a dihedral angle of 60 degrees, but methyl hydrogen gauche-butane interactions are not worth anything. So there's no gauche-butane interaction. No gauche-butane interaction there either between the two H's. None there, none there, none there. But wait, we've got these two methyl groups that have a dihedral angle of 60 degrees, and they're both bigger than hydrogen, so we have one CH3 gauche-butane interaction. So I'll just abbreviate that as GB. CH3 gauche is worth 0.9 kcals per mole. So 240, we've got this CH3, so that's one gauche-butane interaction there. CH3H, that's not one. HH, nope. HH, nope. And HCH3, nope. Okay, so just one gauche butane interaction there, which is also worth 0.9. So 240 and 120 will have the same energy. And then 300 is eclipsed. Okay, so let's talk about these eclipse interactions. So there are two types of strain with eclipse interactions. First is another type of steric interaction. So gauche butane interactions are another type of steric interaction, except they have those special circumstances. Something that's true of all steric interactions is they increase in energy as the groups get bigger. That's just a fundamental concept of all types of steric interactions. Now, eclipse conformations don't have gauche butane interactions because they don't have dihedral angles of 60 degrees, but they have two types. So van der Waals interactions between the atoms that are knocking into each other, because when they have a dihedral angle of 0 degrees, they're much closer to each other. But you also, so atoms contain electrons, their electron clouds repel each other. But you also have bonds that are eclipsing, and bonds contain electrons too. And so those are also going to repel each other, and that's called torsional strain. So you've got strain from eclipsing bonds and strain from eclipsing atoms. So, but we don't account for their energies separately. We just collectively call it the eclipsing interaction and say it has a certain energy. So let's look at this 60 degrees. So you have an HH here eclipsing, so we have one HH eclipsing there, and then you have a CH3H here and a CH3H here, so two CH3H eclipsing interactions. So the value for HH is approximately 1 kcal per mole, and then the value for CH3H is 1.3, so that's going to be 2 times 1.3, and so we're going to add these up. So 2 times 1.3 is going to be 2.6, and plus 1 is 3.6. Okay, now let's look at 180. So here we've got HH and HH, so we've got 2 HH worth 1 each, 2 times 1, plus we have 1 CH3CH3, which the table on page 21 of your lab manual says is 3.3. So if we add these up, we have 2 plus 3.3, so 5.3. Okay? And then now we got to do 300. So we've got 1 HH, CH3H here, and a CH3H there. So if we have 2 CH3Hs and 1 HH, that's going to have the same energy as 60 degrees. So that's going to be another 3.6.
So now let's talk about how to find the anti-conformation. So the anti-conformation is always going to be your lowest energy conformation. However, you do not need to calculate the energy values in order to find the anti-conformation. Instead, another definition is that it's always going to be a staggered conformation, and specifically it's going to be the staggered conformation where the bulkiest group on the front carbon and the bulkiest group on the back carbon are 180 degrees from each other. So in other words, they're as far apart as possible. So bulk is a factor of two things. It's a factor of, first of all, like the length of, particularly we're talking about alkyl groups, the length of the carbon chain, but also, and more importantly, the degree of branching. So like all else being equal, the more branched a group is, it's going to be bulkier. Getting back to this example, what's the bulkiest group on our front carbon? Well, we've got 2 H's and a methyl group. So of those 3 things, the methyl group is going to be the bulkiest. Now let's look at the back carbon. The back carbon also has 2 H's and a methyl group. So the methyl group is definitely the bulkiest of those. So we want to look for the conformation where the methyl group on the front carbon is 180 degrees from the methyl group on the back carbon, which is going to be this one right here at 0 degrees, which makes sense because its value is 0. But you didn't need to calculate that.
Okay, so now we've got our energy values, so I am going to erase all of these Newman projections so that we have room for a graph. And I'm not going to draw the Newman projections on the graph because then we would run out of space. And now we're going to make our graph. Okay, and I'm going to put labels on it. So down here we have dihedral angle in units of degrees. And then up here on the y-axis we have delta E in units of kcal per mole. So I'm going to try to make these as evenly spaced as possible. So 0, 60, as evenly spaced as possible without actually worrying about it. And then now let's mark off our values. So we're going to make the 0 point be there, and then I'll just draw a dashed line, and then 0.9. I'm going to try to make these, oh, that's not degrees, 0.9, 3.6, 5.3. Not quite perfectly evenly spaced, but we'll deal. So 0 degrees is 0, and this is 3.6, 0.9, and then 5.3. And then 240, 0.9, 300, 3.6, 360 is going to be 0. Try to make these rounded, but it doesn't have to be perfect. Okay, so our energy diagram is going to look like that.
You guys follow your model kit's instructions because they will most likely be different unless you have the same exact model kit that I do, which you probably don't. So, okay, so I've got an sp3 hybridized carbon atom. Make sure you're using an sp3 hybridized carbon atom. That's going to be, I'm going to make that my front carbon. Okay, so, and that's the one that the arrow from the eyeball is pointing to. That's the front carbon. So notice how that one has a CH3 pointing up. So, all right, we've got the CH3 pointing up and then another CH3 that's down into the viewer's right. So that is going to go here. And then we've got another we've got an H. It's coming out at you because it's wedged, so that means coming out at you. So that's going to be here. So now we just need to put in our back carbon, and again, with my model kit, carbon-carbon bonds are the white ones, and the pink ones are CH bonds, except, I mean, it also matters that you put the correct atom on the other end, but yeah, just remind you that came from the instructions. So there's going to be my single bond to my back carbon. Okay, so this is going to be my back carbon. Pop that on there like that. Okay, and I'm not going to worry about the orientation for this one just yet. We'll rotate that at the end because there's free rotation about sigma bonds, so it's not a big deal. But what does it have on it? Well, it's got 2 hydrogens and then this bond to a third carbon that's got some other stuff on it. Okay, so so I've got this, and again, I pre-assembled it. So there's one CH. There's another CH. And then we need a carbon-carbon bond to a third carbon. Okay, and that's going to have what on it? Well, that's got 3 H's, so it's just going to be a CH3. So I've got one of those handy from what I took apart before, so that's going to be my third carbon. So now let's rotate this. Let's worry about the rotation. So we're looking at it from this direction, and so we've got CH3 pointing straight up. So there we go. Okay, so we've got a CH3 that's pointing straight up in the front. We just tilt that a little so that it looks that way. There we go. And I'll take still photos of this because ultimately I can get the angles just right. So then we've got a CH that's down and to the viewer's left, and then a CH3 that's down into the viewer's right. Okay, so that's the front carbon as I'm looking at it. Now, the second carbon here, which is going to be our back carbon in this case, that has a hydrogen pointed straight down. So now we've got one pointed straight down, and notice how it's like opposite in direction from the CH3 that's pointing straight up. And then we've got another hydrogen that's up and to the viewer's left. And then behind that, we have a CH3. Okay, so this is how this thing looks. And again, don't worry, I'll take stills. We're looking at it like this, where this is our front carbon, and then that's our back carbon behind it. So that is what you're being asked to draw the Newman projection for structure A. Okay, now let's build structure B. So once again, going to start with a tetrahedral carbon atom. What does it have on it? So that's one our eyeball is pointing to. So that has an H pointing straight down, so just a singly bonded hydrogen pointing straight down. And then we've got a CH3 that is up into the viewer's left. Sorry, gotta make sure that stays pointing straight down. So that's our CH3, and I pre-assembled that CH3. And then we need another CH3 that's going to be up into the viewer's right. Okay, so that is what's on my front carbon, but we also have our bond to the back carbon. So we got a CC bond there behind it. Maybe I can turn this like sideways so you can see what I'm doing. Okay, and then we need to worry about what's on our back carbon. I'm not going to worry about the orientations just yet because we can rotate about the carbon-carbon single bond pretty easily. So that one's got a hydrogen stuck to it. So hopefully this back carbon, it does. It has 2 H's, so perfect. This pink CH bond thing is stuck to it. So I'm going to make this my back carbon. Okay, so, oops. That's going to be my back carbon. And like I said, we don't need to worry about orientation just yet, but we know that one of those is pointing straight up, so just do that. And then it needs its little atom at the end of the bond. Okay, so that's our H atom on the back carbon. And don't worry, I will hold this in the correct view at the end. So and now we need another hydrogen. and a CH3. So there's another H. Okay, and then we have a CH3 on there as well. So we've got an H, and a CH3. Okay, so here's a CH3, and I'm going to take one of my carbon-carbon single bonds, and I am going to pop that guy onto the back carbon. Okay, so there's our front carbon. Right, notice how we have our H straight down, and then our two CH3s up and to the side. So on our back carbon, we have one hydrogen pointing straight up, and then we have down and to the right, we have a CH3. So actually that's got to be your right, not my right. So there we go. And then we've got an H that's down and to your left. Okay, and now for structure C, on the front carbon, notice how it has one H and two CH3s, just like the previous one, so we can maybe reuse that, but we'll see. And then the back carbon has two H's and a CH3, so just like structure B. So we don't actually need to rebuild our model. We can use the same model, but we do need to rotate it so that it's in the correct view. Okay, so here's our front carbon, that's the one with two CH3s and the H. So we want to rotate that such that we want an H pointing straight up, because that's how it looks in the picture. And then we've got down and to the left and down and to the right, we've got methyl groups, so CH3s. Okay, so that's the front carbon. Now the back carbon. So on the back carbon, we've also got a hydrogen pointing straight up. So, and then we've got a CH3 that's down into the viewer's right. So I am going to put the CH3 like that. And then we have an H that's down into the viewer's left. Okay, so that is what this looks like. Don't worry, I will take stills like I do with all of them, but just to show you guys, that is what it looks like. So that's C.